Length contraction, time dilation. These are two of the most mind-bending ideas in all of physics. And we usually get to them by following Einstein's famous thought experiments about chasing beams of light. But what if there was another way, a more fundamental path to that same strange reality? Well, in this explainer, we're going to do just that. We're going to derive these core concepts of relativity using a law you probably learned in high school, the conservation of energy.
Okay, so our roadmap for this comes straight from chapter 12 of the book Newton and Relativity. Now, here's what's so fascinating. The book, in the chapters leading up to this, has already built the framework for relativity without ever using the idea that the speed of light is constant for everyone. So we're already starting on some pretty unique ground. We're going to build a bridge from the physics we know and see every day right into the heart of relativity using just one single unbreakable rule. Energy is always conserved.
All right, to kick this off, we need to set up a very specific scenario. So let's get the stage set for our thought experiment.
Here's the blueprint. Picture two electrons. They're zipping towards each other, both at the exact same velocity, which we'll call v. They start out separated by a total distance of 2L. And their destiny? They're going to smack right into each other and merge, forming a single new particle. Simple enough, right? Now let's put ourselves in the shoes of our first observer. We'll call them O. For observer O, who's just sitting still right where the collision is going to happen, everything looks perfectly balanced, perfectly symmetrical. Each electron travels a distance L over a time t. It's just textbook physics, distance equals velocity times time. No problem.
But here is where it gets really interesting. We're going to introduce a second observer, O prime. This observer is also moving at that same speed v, but they're moving upwards at a right angle to the electrons. Now, from their moving viewpoint, the collision doesn't happen at the center anymore. To them, it looks like it happens at a shifted point, a different distance we'll call L prime.
So let's just pause and compare these two views. Observer O sees a clean, simple, head-on crash. But observer O prime, our moving observer, they see the electrons coming in at an angle with a totally new speed, v prime, and they see the collision happen at a different spot, L prime. And that right there, that's our central puzzle. How on earth do we figure out these new values, L prime and v prime?
Well, we can pull out some simple geometry to get us started. For observer O prime, those velocities form a perfect right-angled triangle. So using the Pythagorean theorem, we can write down this nice little equation for v prime squared. But hang on, look closer. We've got a problem. We have one equation, but two things we don't know, L prime and v prime. In math, that's a classic dead end. We're stuck, unless we can find another equation. So before we go hunting for that second equation, let's just see what happens if we try to solve this using the physics of our slow-moving, everyday world. Let's see where our intuition takes us. In the world we're used to, we just assume that the velocity components are equal. That would make a perfect 45-degree angle. And the conclusion seems pretty obvious, right? The shifted length, L prime, it just has to be the same as the original length, L. In this view, there's no weirdness, no contraction, it's all neat and tidy. But, and this is a huge but, this simple, intuitive answer leads to an absolute disaster, a paradox that breaks the universe. If L prime really equals L, then the math says the new velocity, v prime, is about 1.4 times the original velocity, v. So what happens if those electrons are already moving at, say, 80% of the speed of light? Well, our calculation says v prime would be faster than light, and that's just not possible. The universe has a speed limit. So our everyday intuition, it completely falls apart right here. We need a better tool. Since our trusty old geometry led us into an impossible situation, we've got to bring in a higher power, a law of physics that holds true for absolutely everyone, at any speed, no exceptions. And that's where our hero comes in, the law of conservation of energy. It's one of the most fundamental rules of the cosmos. Energy can't just be created out of thin air, and it can't just vanish. The total energy you start with in a system has to be the total energy you end with. It's non-negotiable. And this beautiful law gives us our golden key. See, we can write down the total energy for each observer's point of view. On one side of these equations, you have the energy of that new particle that's formed after the collision. On the other side, you have the total energy of the two electrons before they smash together, which includes their rest mass and all that kinetic energy from their motion. The most important thing here, both of these equations have to be true at the same time. This is the second relationship we needed to crack the puzzle. So let's follow the logic down the waterfall. First, we basically just plug one of our energy equations right into the other one. Then we do a bit of algebraic cleanup, expanding and simplifying, and then we solve for v prime. And look at what we get in step 3. Suddenly, we have a formula for our unknown velocity, v prime, that only depends on the original velocity, v. Just like that, we've eliminated one of our unknowns.
And the waterfall keeps flowing. We take our shiny new expression for v prime and we plug it all the way back into that geometry equation we started with. We substitute it in, we simplify it down, and after a little more shuffling of terms, there it is. We finally have a clean expression for our last unknown, L prime squared.
Okay, we've done the heavy lifting. We've crunched the numbers. Now let's just take the square root of that final result and see the profound, absolutely remarkable reality that the law of conservation of energy has forced us to accept.
And here it is, the big payoff. The shifted length, L prime, is equal to the original length, L, multiplied by this wild-looking factor, the square root of 1 minus v squared over c squared. This, my friends, is the famous formula for length contraction. We just proved, using only the conservation of energy, that for an observer in motion, distance itself must appear to shrink. But it doesn't even stop there. It's a domino effect. Once you have this equation for length, you have the master key to unlock the full Lorentz transformations. And once you have those, another consequence becomes absolutely inevitable: time dilation. For the universe's energy books to stay balanced for every observer, not only does space have to contract, but time itself has to slow down. So let's just recap this incredible journey. We started with a simple experiment. Our classical, common-sense approach led us to an impossible, faster-than-light paradox. So we brought in an unbreakable law, energy conservation, to act as our guide. And what was the result? The only way for that law to hold true for everyone was for reality itself to change. Space and time had to literally bend and warp, all to keep that one fundamental law intact. You know, the authors of our source text put it so perfectly. They say that by simply applying the law of conservation of energy, it becomes possible to derive the formula for relativistic length contraction. No light postulate needed, just one unshakable law. And that leaves us with a pretty deep thought to end on. A basic law we all learn in school, when pushed to its limit, just completely rewrote our understanding of space and time. It really makes you wonder, what other profound secrets about our universe are hiding in plain sight, tucked away inside the laws we think we already understand?